In this lecture, we'll look at a real application of floating point computation, and we'll do that to illustrate how we use the floating point operations that are available in RISC-V to do a real-life computation. And we'll do that by looking at a matrix multiplication example. Matrix multiplication is a very important operation, has always been, but in the recent years it became even more important because matrix multiplication is one of the fundamental operations that are needed for deep neural networks that are used in deep learning. Because of this resurgent interest in matrix multiplication, several specialized accelerators have been produced to accelerate both training and inference in these networks. So they are usually called TPU for tensor processing units, and they have been produced by many different companies, including Google and Huawei, Apple, and Amazon, and others. And more recently, specialized accelerators for matrix multiplication are being included in standard commercial processors. IBM has announced that the upcoming Power 10 processor will have a specialized matrix multiplication unit. And actually, my research group here at the University of Alberta has been working for a couple of years now with IBM developers and researchers to try to produce the best code possible. We work with in compilers here in Alberta, and we are trying to help them produce the best possible code to do the best utilization of the matrix multiplication unit that will be available in these processors. They are called MMA for matrix multiplication accelerator. But in this lecture today, we're not going to delve in the 20 plus years of research on improving the performance of matrix multiplication, which involves the memory accesses that you do and how you do tiling or blocking in order to improve the performance of the algorithm. What we're going to do instead, we're going to present what is usually known as the naive matrix multiplication algorithm. Is the one that simply performs the multiplication. And that will be sufficient for us to illustrate how we use these floating point operations in a real application. So our example is a matrix multiplication example. Our matrix multiplication will produce a matrix C that is the result of A times B. It's called double precision matrix multiplication. Let's assume that C, A, and B are all square matrices with 32 elements. Of course, we could extend this to a generic size matrix, but we're just trying to keep the code simple here because we're going to be producing assembly directly. So we have three arguments to the function mm. That's my matrix multiplication function. The first is a pointer to matrix C, and then I have pointers to matrix A and B. I use a special type that I use a defined type size T, and I have three index variables of the type I, J, and K. My outer loop for the matrix multiplication is the loop I. That is a loop that is going over the rows of the matrices A and B, and J is going over the columns. So I is going over the rows of matrix A, J is going over the columns of matrix B, and then I initialize Cij to 0, and what I need to do to compute the value of each one of the Cij elements is to accumulate the product of Aik times Bkj, and I need to add that Cij. So that's how I compute each one of the Cij elements. This notation here is an abuse of notation in the textbook because in C you cannot have multidimensional pointers like this, so you cannot skip the size of the previous dimension. You actually would have, if I had matrices here that were of arbitrary size, I would have to be passing as parameters to the sizes of the matrix. And the assumption that I'll make here is that the base, sorry that there's a cut there, maybe if I change the view in this slide here, it will be better. So this version is better. So the parameter passing here is that the base of the matrix C is in A0, A is in A1, and B is in A2, as is the convention for passing parameters in RISC-V. The other assumption that I'll make is that my indexes I, J, and K will be in the registers S0, S1, and S2. So here's my code for my C code for matrix multiplication, and to generate assembly code, the first thing that I would do is to create a block diagram for this code. This block diagram starts by initializing the variable I to 0, and then it will check to see whether I is less than 32. If I is less than 32, I can then initialize J. I ask whether J is less than 32, and then I initialize the Cij element of the matrix to 0, 0, and I initialize my index variable k to 0. And now, while k is less than 32, I will do the operation that is in this line in the C code. To do this operation, I need to load the value of Cij, and then I need to load the value of Aik, and I need to load the value of Bkj, and then I can do the multiplication followed by the addition, and then I can move the result into Cij. And then I will increment k, and I'll go back and test the value of k, and then I will increment j, and I'll go back and test the value of j, and then I will increment I, and I'll go back and test the value of I. So this, and then when the value of I reaches 32, I will return. So this would work fine, and it is a good computation, but note that in the innermost loop here, I am loading the value of Cij and storing the value. This is a store operation here, and I'm storing the value of Cij in every iteration of the loop. Do I need to load and store the value of Cij in every iteration of the loop? And the answer is no, I don't need to if I use a temporary. So if I create a D2 here, initialize D2 to 0, I can simply keep adding the value of this D1 to D2, and in the end, when I'm done with the inner loop, I can store the value of Cij just one time. So I do not need to load the value of Cij anymore, because I can use this temporary, and that will save me instructions. And again, those are my assumptions. So now I can start to generate code for this. I'm gonna get out of the way when I need to. So first I'll put the number 32 into T1, then I put 0 into I, and then I will do my initial test here. I'm asking whether I is less than 32. This is a branch greater or equal unsigned. And then I initializing J to 0, and then I checking whether J is less than 32, and then I initializing what was the 2 here. I'm gonna use the floating point register F4 for the 2. So those are registers that we haven't used too much in 229 yet, because we haven't worked much with floating point numbers yet. And then I tested to see whether k is less than 32, and then I'm gonna have a loop body. So this is a common way to encode the loop, is to, when you get to the loop body, just say there will be a loop body in here. I'm gonna worry the loop body later, because I'm right now worried with creating the control flow for the loops. This actually is a good practice to generate code. So then I had to increment k, and I jump back to L3 where I test the value of k. And then I need to take the value of F4 that was generated by the loop body, and I will store it in Cij. I will increment j and go back to L2 to test the value of j, and then I'll increment I, and I'll go back to L1 to test the value of I, and then I'll be done. Here is my D1 label. So this code here does not do the full computation, but it creates the data the control flow structure that I need for this code. However, in this code, we have quite a bit of tests that we do, checks and jumps. So there are 3 jumps here that I need to jump back to the beginning of every loop. We have seen that we can do the check at the end of the loop and save a jump. And in this case, actually, because I know that the size of the matrix is 32, I know that these loops are gonna execute multiple times. So I don't need to have what we call a guard branch to test whether I go into the loop at all. So I can generate better code in this case by simply initializing I, j, k, and the 0 in the beginning without testing anything, and then performing the body of the loop. And after I perform the body of the loop, I can increment k, and then I can test to see if I'm done. If I'm not done, I go back to the body of the loop. If I'm done, then I store the value of the 2 into Cij, and I increment j, and I test, and I go back to the element of the loop. And finally, I increment I test, and I go back, or I return. So as you can see by the block diagram, I have much fewer control flow instructions because I don't have the test in the beginning of the loop and the jump at the bottom. So this is my assumptions again. And now if I start generating code for this code, I start by initializing T1 with 32, and then I need to initialize I with 0, J with 0, and then I initialize F4 with 0, 0, and then I initialize K with 0. Once I have done that, I have my loop body, and now I need to increment J, and I test now whether it's less than or unsigned. To go back to L3, I store the value of Cij, and then I increment J, test to see whether it's less than 32, increment I, and test whether it's less than 32, and this is the end of my code. You can see that this country structure is simpler than the country structure that we had before. This is a 3-nested loop, and in a multiple nested loop, it pays off to try to find a country structure that is simpler and thus less expensive. So now that we have all that, remember every time we said, well, there is a loop body and we're going to worry the loop body later. So now it's time for us to look at the loop body. So how do we load the value of AIK? Remember, we're going to have to load the value of AIK, BKJ, and store in CIJ. So how do we load AIK? First, we need to consider how a two-dimensional matrix of doubles is stored in memory. And this is a drawing of how we store it. We store A00. Next to A00 comes A01. I am assuming a row major matrix order. So we store an entire row first in memory, and then the next row, and then the next row, and so on. So memory grows in this direction here. So in this case, what we have is that this is the base of A. This is the base of A plus 8. And this is the base of A plus 8 times 32 because there are 32 elements in a row. So the distance between this position and this position is 32 times 8. And because each element has 8 bytes, because my matrix is a matrix of doubles. And in general, to access the element AIK, I need to do the address of AIK will be the base of A, so this is the vector A, plus I times 32. So how many rows down? For each row that I come down, I have to go 32 elements. So I times 32 plus K, so that brings me here. And then I multiply by 8 because 8 is the number of bytes in each of the elements of the matrix. So using this expression, so here's my expression, the address of AIK is the base of A plus I times 32 plus K times 8. So the RISC assembly to do that load will be, I do a shift left logical immediate of 5 because I need to multiply by 32. This is because of the size of my matrix. In this example is 32. And then I add K to that. And now I need to multiply this by 8. So multiplying by 8 is a shift left immediate of 3. And then I'm gonna add this to the base address of the array A, and that gives me the address of that location. And then now I have to do a load from that address, but it's not a load word because that's a floating point number that has 8 bytes. It's a double. So the instruction to do that is float load double, FLD, and I provide the address and the register. It will put the value into the register F1. For BKJ, it will be a very similar situation, but now I need to multiply K by 32 instead of I, and then I need to add J to it, and then I need to multiply the result by 8. Then I add this to the base of the array B, and then I do a float load double from that address into F2. So now I have the values in F1 and F2. Also, we have loaded AIK and BKJ. We can proceed to perform the multiply and add operation. The multiply and add operation is simply fmuld, that is the double version of the multiplication. And the add is an fadd, that's the double version of the addition. So all I need for the actual computation is those two operations. Now, to initialize and store F4, you only all you need to do is to use an fconvert instruction. So this is converting from a word to a double, and in this case I'm converting the value of the register 0 to F4. That gives me 0 in double type. And to store, therefore, in AIJ is very similar to the loads that I did before. I have AIJ, so I need to multiply I by 32. I add J to it, I multiply by 8, and then I add this to the base of the array, that is the address of C, that was in A0, and then I now do an FSW, that is a float store double, and that will write the 64 bits, that's 8 bytes, into the address that was specified. So here is this code is not complete. Of course, I'm using S registers and I'm not showing the code to save and restore the S register, so I'm not showing the stack manipulation code here. But you can see by looking at this color code here, this area is the area where I do the load of AIK. This area in the code is where I do the load of BKJ. This is where I do the multiply and add, and this is where I do the store of the CIJ. So this illustrates how I would perform. Again, this is a naive version of matrix multiplication. This matrix multiplication, as implemented, we would have a very poor performance compared with very optimized matrix multiplication that we can do through a sequence of compiler transformations or using one of the specialized libraries that we have for matrix multiplication.